right, good morning, everyone. I hope you got some rest last night. So let's see. Today's the last day of lecture time where I'll be presenting slides and talking about new material. Starting next Monday, as I stated yesterday, we'll get into group presentations. If you want to know about the kind of the format for the group presentations and some of that, I talked about that yesterday. So if you could just go back and watch that lecture again, if you either were not able to attend or didn't watch it already. So what we'll do today is we'll complete our design phases of database design. So the last phase that we'll talk about will be the physical design. So, and this does include literal physical aspects of the database. So actual like server and other types of hardware, but physical also will include in that the software as well, in the sense that what RDBMS are we going to use. So many of you have been using MySQL for this course for your group projects and kind of put data in for your example data for your homework assignments and stuff like that. And so you're used to MySQL, but MySQL is not the only database system that we can use. There's lots of other options. There's kind of more costly ones, but come with a lot of nice things like security features and stuff, like Oracle is an example. There's others. There's Sybase, SQL Advantage. Microsoft has a SQL Server. Yeah, there's all kinds of options for databases. Some, I actually met a guy a few years ago that his company found that none of those options out there were really going to satisfy their needs, and so they took the time and the effort to create an in-house database system. So it was a non-SQL based database system. So sometimes we find that there are certain things that we need our database to do that none of the existing solutions provide everything that we need, and we might create our own. That's probably pretty rare. I would imagine that that's probably not common, because what usually happens, as we'll talk about here today, is that we kind of look at what our needs are, and we kind of break them out into what you could call negotiable and non-negotiable items, and even within that, there's kind of like absolutely must have, really want to have, kind of would be nice if we had it. There's different ranges of that, and those things that are absolutely must have, if a certain database management system solution does not provide that for us, then we say we cannot even consider that one as an option. Okay, but basically, at the end of the day, what we have to do is we have to kind of look at the trade-offs, look at the different features that come with some of those different database management systems, and decide which ones are so important that we have to have them, and which ones can we say, okay, if it has it, great. If it doesn't, we'll figure out a way around it. Okay, so let's get right into it. Come on. Okay, all right. So remember, the last phase we talked about was that logical phase, and if you remember, hopefully you also remember the phase that came before that was that conceptual phase. And remember what I said kind of way back towards the beginning of our design discussions, is that the output of each phase kind of serves as the input to the next. So the conceptual phase, its output was the ER diagram, and then the logical phase, what's going to happen is we're going to take that ER diagram, that ER model, and we're going to use it to determine what types of relations should there be. And we talked about kind of how the different relationships might result in like sometimes like that one-to-one mandatory on both sides relationship, two entities in our ER diagram, but only one relation, only one table in our final database. Another example would be you have two entities and with a many-to-many relationship between them, and that results in a third table, so that not only do we create a table for entity 1, we create another table or relation for entity 2, and then we also have, remember what I called that in-between table, that middle table between them that represents a linking between them. Okay, and so sometimes two tables with a relationship between them in our ER model will result in only one table in our final design. Sometimes it'll result in 3 tables. Sometimes it'll just be the 2 tables with a foreign key, right? And so, but hopefully you have understood based on our logical design how we can take that ER model, represent what relations we need to create, and then we end up with not a schema, like gosh, I can't remember the name that the slide used for it, but basically kind of a table of all the different, what the tables are, what the columns are going to be, and what some of those, what primary key is there going to be, what foreign keys, and what other information like alternate keys might be. And remember, one of the things I said in that is we're getting closer to SQL, but we're not there yet. Right, because what we're trying to do is we're trying to take that visual ER model and we're trying to now come to a place where we can get closer to somebody could take this thing and write some SQL scripts and make the database tables that we need. So remember when I said that the alternate key, what does that mean? That means that it could have been a primary key. We're not going to use it as the primary key, but we do know something about that column, which is what? That it needs to be unique. So when we come to creating those SQL scripts, we can put a unique constraint on that column. We know that that's going to come in there. Okay, and again, another big part of the reason why we don't want to write SQL as part of the logical phase is because we don't know if we're going to an SQL database or not. We probably are. I mean, I would say that the majority of database systems out there rely on SQL-based databases because it's just the industry standard. But there's not every database is an SQL database. And what we want to be able to do is we want to be able to take the output of that logical phase, that set of definitions, table definitions, and columns, and all of that. And we want to be able to take that and put it into whatever database system we decide to use. And that's what the physical database design is all about, is about us helping us to understand, okay, what database system do we need to use? Do we need to go with MySQL? Do we need to go with something heavier like Oracle? Do we need to go with something else entirely? Okay. All right. So here in the slides. Yeah, so if the logical database is concerned with the what are we trying to create, the physical is more concerned with the how. How are we going to go about doing that? Okay. All right. So again, we'll talk about here the base relations, file organizations, and indexes. I won't get into that too much with the file and indexes, but we will talk heavily about what two things are what I want to focus on today. Are the derived data, because that's really important. There's 2 different ways to represent derived data, and then we also will talk a little bit about indexes and what those are and how they're used. Okay, but basically the steps for the physical database design part is we're going to take our logical data model. We're going to design our base relations. We're going to figure out how we're going to do derived data. And we're going to design some general constraints. We're going to analyze, in step 4, we're going to analyze our transactions, file organizations, and indexes. estimate disk space requirements. And again, part of the reason why I won't go into the file organizations and the disk space stuff so much in detail in this is it's good to kind of have a kind of an overview idea of how that stuff works. But really, for the most part, unless you're planning on becoming a database administrator, which is a fine career. If anybody in here is really loving database stuff, that would be a fine career for you. But unless you're going to become a database administrator, most of us, like I was a client-side programmer that connected to the database, really don't have much need to know the finer details of this. Okay. Now, one thing we do need to do as client-side programmers is understand how to design our user views, because that's what we're going to be, that's how our users are going to interact with our database. Also, as part of this physical, we're going to be trying to understand security mechanisms. What security do we need and how are we going to do that? Knowing that we don't have to do, hopefully, we don't have to do all of the security stuff ourselves. Like, we don't have to reinvent the wheel on this. There's a lot of security done out there, but we need to take advantage of what mechanisms are available. If hashing is available, if other types of encryption are available. I was reading an article a couple of days ago about how there was a company that was basically storing all their passwords, including their administrator passwords, in the database in plain text format without encrypting them, which is very dangerous. So, go ahead and use those security mechanisms that are available to you. You don't have to write the encryption algorithm yourself if one exists, but you do need to make sure to use it. So consider the idea of controlled redundancy. We'll talk a little bit about that. But monitor and tune. Probably the majority of your time, if you stay with a company or with a system for a long period of time, a lot of your time is spent just in maintenance. Like not a ton of time is spent in creating new software. A lot of time is spent in maintaining what already exists and keeping up to date with security and other needs as well. Okay, especially as things get bigger and much more data heavy, then it becomes slower if we just leave it as is. And so we need to be able to make sure that our users continue to have the same experience, the same speed, and hopefully things get even faster as we monitor and tune that system. Okay. I don't know what that was. All right. So some questions that you may want to have is making sure and question whether or not the DBMS that you're wanting to use, whether or not it supports certain things like primary keys and foreign keys. Well, we would like to have that be supported. That's if it doesn't support primary key and foreign key, it's probably not a relational database to start with. Kind of the whole point of the foreign key is to show that there's a relationship between one table and another, right? So we need to check, okay, does it support this? Do we need it to support this? Okay. Required data, does the system support things to be not null? Yeah. Because if a piece of data is required, if a type, like a column or an attribute is required, then our system needs to be able to support not null constraint. Okay. Other domains, does it allow for saying that it has to be within a certain domain? Some of you, like I said, have learned that MySQL does not support the check constraint, and so a domain would be certain types of domain constraints would not be possible with a MySQL database, right? So if that's something that we absolutely need to have, then MySQL might not be the system for us. But note that uh, even if a system, if a database system does not support something like that, like let's say the check constraint is check that salary is greater than 0. You know, if you're putting like a salary column for our employees, well, MySQL might not be able to support that, but what if we need to have that as part of our system? We can do what? We can put that constraint into our client side code, right? We could put that as part of a check, but that means that's more work. That's more work for the client programmer, right? And that's one of those things that we have to ask, is that's a trade-off. Right? The client programmers in the room will say, no, we need to have a database system that allows this, that I don't have to program this, right? Because the client programmers, they don't want to have to write the code for this if they don't have to, right? The managers in the room might say, yeah, but MySQL is free to use, right? Or cheap if we're maybe using a more enterprise version of it, right? But MySQL is cheap, and you guys are just trying to get out of doing work, right? And so that's that trade-off is does the cost savings justify the extra work on the programmers? And if the answer is yes, then we can go with that cheaper database management system, and we can put more work onto the programmers. If the answer is no, if for whatever reason, maybe the domains are changeable, all right, maybe in the sense that over time the domain constraint might change frequently, and it'd be a lot easier just to do a simple quick update on the database column rather than having to do it through the user interface or through the client side. Then that maybe we might want to go with the more costly system. Again, there's no, for anybody here who's saying, well, what is the right answer? Which one should I choose? There isn't one. Okay, it's not that it's always going to be you have to go with the DBMS that provides everything. It's not going to be you always need to go with the cheaper DBMS. It's sometimes some particular projects are going to need option A, some other projects are going to need option B. Okay, let's skip over this. So let's kind of get to, because I want to get to the derived data discussion before the break. So for each relation, we have from our logical model, we have the name, so we already have that from the from the logical data model. A list of simple attributes, we already got that. The primary key and where appropriate foreign keys and alternate keys, we already have that, right? Referential integrity constraints for any foreign keys identified. So all of this, right? All of this comes from our logical model. We talked about this yesterday, right? This was where the referential integrity constraint, remember, that is that what do we do on update, cascade, default, whatever, on delete, what do we do? That's the integrity constraint. That's the referential integrity constraint that we're talking about. So all four of these things came from our logical data model. Okay, but now there's some more stuff we need to figure out, right? Because what are we missing here? Like, just for our attributes example, what did we not have in our logical data model discussion? Do you remember? Are you awake? All right. Well, I think we're still waking up, so that's okay. But where are you? Why is it not coming up? Okay, there we go. All right. So for each attribute, all we had was the name of the attribute. That was it. And we had what the primary key was, stuff like that, right? But now for each of those attributes, we need to know what is its domain, what is its data type, length, and any constraints. So, is a certain attribute, is city going to be a string? Probably, right? Is let me see, phone number. Phone number is a very interesting one because it's stored in so many different ways. So sometimes a phone number can be literally a number, right? Sometimes a phone number can be a string. Sometimes a phone number can be multiple pieces of string. So, or numbers, multiple numbers, or multiple pieces of string. And so, pieces of string, multiple string values. So if you think about it, many of you, like me, have your phone number starting with 5, right? So 05. So we don't really need the 0 because that's part of the country code. But that first set of numbers, 531, for example, right? And that first one, 531, then there's 3 more numbers, 1, 2, 3. Then there's 4 more numbers, 1, 2, 3, 4, right? And we could store that as one long 10-digit number. We could store that as one 10-character string. We could store that as 3 numbers or 3 strings. One 3-character string or number, one 3-digit string or number, one 4-digit string or number, right? And so there's all kinds of different ways that the different systems deal with the phone number storing, right? Which ones are better than others? It depends. And my guess is that the reason for all the different ways of storing them is because different systems require different needs, right? I can tell you that it's easier for a database to search numbers than it is to search strings. And so for that reason, if you want something that's going to be able to search quickly through phone numbers or sort them quickly, numbers could be better. Also, if you need a system that searches for that first set of 3 characters to say, okay, what area did this come from, or what cell phone company or what mobile phone company provided this number, right? Then then you may want to store that as a number, because then you could search for that much more quickly, right? Because again, just as I said, it's easier for it to search for numbers than it is to search through strings. It's also easier to search smaller than it is to search larger, right? Searching through a list of phone numbers that are all 10 digits long, right, will take longer than searching through a list of phone numbers where all we're really searching for is that 3 is based on those 3, the 3-digit area code, right? Okay, so all of those different possibilities and trade-offs, but notice also that if we store the phone number as 3 separate values, then that puts what? That puts strain on possibly the user interface, the client side, to put those 3 values together for display purposes, or for if when the user goes to enter their phone number, if they're registering for the system, they're not going to want to type in 3 digits, 3 digits, 4 digits, although I'm sure you've seen websites that have done that. Most likely, we're going to want to give them one field for phone number, right? Okay. So all these are just the considerations we have to decide on. Okay, what is the data type going to be? What is the length going to be? Is there going to be a default value for the attribute? Right? Can it hold nulls? Do we want to allow null phone numbers? Well, for some systems, maybe, yeah. Maybe it might make sense that a user won't have a phone number. For other systems, we say no, they need to have a phone number. Like maybe my account with Turkcell, they're like, yeah, no, you have to have a phone number. It's Turkcell, right? Maybe my account with Hepsiburada might say it's okay if he doesn't have a phone number, right? So those are whether or not it's required or not. And then again, whether or not it's derived and how it should be computed. And we'll talk about that. I think that's here. Yep, good. I got here just in time. All right. So how do we represent derived data? Right. Well, what is derived data? Maybe let's talk about that for a second. So derived data means, and I brought my tablet today so I can kind of draw some of this stuff out if need be. All right, so derived data, derived data simply means data that is derived is calculated from some other source. An example of a piece of derived data that you use every day is your age. All right. You say, wait a second, my age is derived? What do you mean? How is your age derived? Like what derived means is calculated from some, like in other words, derived data is calculated based on some other value or set of values. So, for example, you store some other piece of information, but the data that we're talking about, yep, okay, that's part of it. The Tirana, that's part of it. Your age is based on your date of birth and something else. What is it? What's the other thing? Right, current date, exactly. Because if I only know it, let's say I only know your date of birth. Now, I could calculate your age because I also happen to know what the current date is. Right? But let's say I were to say, you know, just if I were to want to pick just figure out your age on any given date in history, I would need to know that date and I would need to know what your date of birth is, right? So your age is not something that's static. It's not something that stays the same over all time, right? Your date of birth, however, does. Right? Your date of birth will never change. Okay, I mean, my son's getting into discussions about, you know, alternate universes. He's been watching lots of Marvel movies and he's talking about alternate universe. So maybe in some other alternate universe you were born on a different day, but we're working with this universe. Let's talk about this universe. Your date of birth will never change. Okay, but your age will. And when will your age change next? The next time that your birth date, month, birth date, day comes to pass, right? And so the question would be, and this is why we need to talk about this, about derived data, is how do we store derived data? Because the university wants to know your age. The nation, Turkey, wants to know your age. Different other services want to know your age. The museum, a few months ago, was it a few months ago? I can't remember the last time I got out, but it was sometime recently, I'm sure. But we went to a museum, right? And you know what the museum has? The museum has this nice thing where if you're up to a certain age, I think it was like 5 or 6 years old, you don't have to pay. My youngest son doesn't have, I don't have to buy a ticket for him. Right? It's very nice. They want to know his age so that they can know whether or not he needs to be paying to enter the museum. Right? How do they calculate that? What is the current date? What was his date of birth? Now the question is, do these different systems, let's say that, and the way that they calculate, the way that they find out what his true birthday. They don't just ask me, right? Well, they could. I mean, maybe they do sometimes, but they don't just ask me, oh, when was he born, or whatever, or how old is he? There's a way they can look it up. They can look it up in the Turkish registry, right? He has an ID in the Turkish system, in the Cumhuriyet. He has what's called an ikamet, right? And in that system, I've registered his birth date, so they can look him up. So then the question I say is, here's what I'm getting to. In that Turkish system, in the university system for you, do they store your birth date only, or do they store in a second column your age? And what are the benefits of storing the birth date only? What's the benefit of storing the age as well in a separate column? Okay. And that's what the discussion of derived data is all about, is trying to figure out how do we store it, how do we store it? Let me see, let me get rid of this. I'm gonna come in here and try to draw some stuff here. We'll see if this works. Okay. All right. Join that. Okay. All right, let's see. Because what I'm trying to get to is, what I'm trying to talk about, and I would agree with you in most situations. Yes, that Tarana, I think you're right. As far as the age being an example, you're right. Because age is frequently changing, it's probably a good idea to store only the birth date. So here's the discussion I'm trying to get, and maybe drawing it isn't going to be too helpful, but we'll see. Okay, so let's say that we have this this table, and we'll call it a person. I don't know. Right. So it's this table that, among other things, name and other things. Right. We're going to also store. We need to know what their birth date is. We have to know what their birth date is in order to calculate their age to start with, okay? So the question is, and change to a different color for this. The question is, one of the things we really want to know is their age. Okay? Is how many years old is this person? All right. Now, if we store this as a column, then what happens is, I'm going to draw in an even different color. Okay, this is our little computer to represent our user interface part of this. Okay, so this is the client side of this application. So when our client program asks what age this person is, do they get a discount for the museum? Do they are they allowed to vote? Because I don't know about Turkey, but I know in America you have to be 18 years old to vote. You know, just different things that as you get old, or hey, even recently, right, with this pandemic lockdown, if you were 65 and up, there were certain restrictions on you. If you were 20 and below, as many of you in this class probably are, there were also restrictions on you, right? It was a very annoying time, wasn't it, to be young, right? Fortunately, I am not in that But my kids are, so it was kind of, not very much fun for them. All right. So the question is, we're trying to ask, is this person 65? Is this person less than 20? Whatever. All right. So if we store this as a column, if we store it as a column in our database, okay, so just get that right there, right? Then what happens? When the client requests that information from the database, it just has to do one thing. It just has to say, what's the value in that column? Simple request, simple response, done, right? But if we don't store this as a column, then that becomes more work on either the client or the DBMS, right? Between the two. Right, and that's a bad drawing of a DBMS. Don't use that. Okay. Because what happens? Either the client has to go get, instead of the age, right, instead of this, either the client has to say, okay, no, give me the birthday and I will calculate the age, date minus birthday, right? Or the client has to request from the DBMS what is the age, and the DBMS has to go get the birth date and then calculate the age. So what I'm getting at is, if we don't store it as a column, it's extra work on some other piece of code to do the calculation. Right? But if we do store it as a column, then when we need to get that information, it's just simple. It's just go out and get whatever value is in that column. All right. So when retrieving the information, when retrieving our derived data, it is easier on the system to store it as a column. Okay. So there, we're done, right? Because that's the only time we ever need data, is to get data, right? Is to when we retrieve data, right? So we're done. We made our decision. We just always need to store derived data as a column, right? Yes. No. Who agrees with that? Who agrees? Yes. Yes. Hojam, you've made a very good case. We should always store derived data as a column. Who says, Hojam, I think you're leaving something out. I think you're not telling us everything. Anyone? No? Okay. I think maybe brains are fried a little bit from this first initial discussion. So since, hey, it's 9:20, so it's actually break time anyway. So let's do this. Let's take a break. So what I've said so far is that when we're going to get data from the database for a piece of derived data, if we store it as just a straight column, age is a column. Then when getting that data from the database, we just got to get that row, get that column value done. Okay, there's no calculation, there's no extra work. We just say, what's that person's age? Oh, their age is 20. Done. Okay. If we don't store it as a column, but we store the other information, birth date in this example, then that requires either the DBMS or the client side requires code to make the calculation in real time. Okay? So if we don't store it as a column, there's extra work, extra code that has to be written to calculate that value. Right? And so what I said was, does that settle the discussion? Does that say that we don't need to have any other discussion? It's harder, more work to get the data when we retrieve it, so therefore we should just store it as an additional column and be done with it. Okay, and Tarana, after the break, we're going to talk about why I left a crucial piece of information out in our discussion of trying to figure out whether or not we should store it as a column or not. Okay, because as we'll talk about in 10 minutes, as we'll talk about, is that getting data from the database is not the only way that a database is used. There's another important part of what we're going to be doing with that data. Okay. All right. So let's take a break. At 9:30, we'll come back and we will continue our discussion on derived data, and I'll see you then.